Here's another example for integration by parts, and this is a special one because we are going to be doing the repeated use of integration by parts within the same problem. So what we're going to do is find our u, find our dv. That part should be the easy part, the algebraic x squared, and dv should then be the trig function. The idea is your u should always be what is eventually going to cancel out. And if you keep taking a derivative of x squared, eventually it'll go away. Sine, if you keep taking a derivative, well, it won't go away. It'll keep on recycling back through. So that's why we're using x squared as our u, and then following the formula, that's what you should get. So now we would try to solve this integral right here. Well, guess what? That ain't happening so easily right now. I don't know how to take the integral of this as it is. However, it's a product. I can do a reverse product rule here. So what I'm going to do is I'm going to do my u dv again. So my u is the algebraic part of 2x, so that means dv is the cosine of x, dx. Integrate cosine of x to get sine of x, and take the derivative of u to get du, which is 2. So now what I can do is I can rewrite all of this. The negative x squared cosine of x stays the same, plus, and now using this formula, uv would be 2x times sine of x, for u times v, minus the integral of v times du. And now I can see I have an integral that I should be able to solve. The integral of 2 sine of x would be negative 2 cosine of x. So that negative out front should become a positive, and the rest just stays as it is. And there you have your answer. Took 2 steps this time, but it worked the exact same. Let's look at one more fun example, and I do call it the fun one. So we're going to go through the exact same process. We're going to start with our u and start with our dv. So u equals dv equals. Now, if you use Lippitt versus Light, this could be a little bit different, but it's going to work the exact same way. I like making my dv e to the x because the integral of that is the exact same thing. U is cosine of x, so dv is the derivative of that, which would be negative sine of x dx. If you had flipped that around, actually it would still work in this case. Remember, Lippitt versus Light, either way should work just fine. So when I rewrite this, uv minus the integral of v du. So v is e to the x, du is negative sine of x. So the negative I'm going to bring out front as the plus. And again, we have an integral that we can't do. So kind of like the last example, we're going to have to do our u dv again. I still have an e to the x, so that should be my dv. So v is just e to the x. That means the rest of this, which is just sine of x, is our u. du is cosine of x. So I rewrite what I have. The e to the x cosine x stays the same, plus this integral, now using this new formula. So u times v, so it would be e to the x sine of x, minus the integral of v times du. And guess what? We got another integral that we don't know how to use. However, what do you notice about that integral? Go back to the very beginning. It's the exact same integral that we began with. We've been saying equals this entire time because we've been making equivalent expressions. So what I'm going to do is I'm just going to rewrite it right here, my original equation, right? Because I just keep on going equals the whole way down. Well, what would happen if I brought this integral right here to the other side? I would have an integral added with the same exact integral. That would mean I would have 2 of that integral. And then I'd have the right-hand side be the exact same of what we just had. How can I solve an integral? Well, how about this? How do I get the integral by itself? Algebra. I would have to just divide both sides by 2, wouldn't I? If I do that, I'm going to have the integral of cosine of x dx. And it's going to equal that big, long expression divided by 2. Don't forget plus c at the end because we're officially done with the problem. So we actually solved an integral without ever taking a legit integral. Kind of interesting, but that's how this works. And when you have a tough one like this, it looks complicated, but actually it's just some very simple algebra to allow you to solve it.